Hello and welcome to 6.4, Graphs of Trigonometric Functions. So today we're going to be examining the graphs of these things. And yes, we have our graphing calculators, and you're going to see actually this graph here, some of these I pulled, came from this calculator, and I stretched it out. It's important to come up with these values, and I will be honest, it's something you really need to memorize. But I think you're going to start seeing a pattern to these values. I mean, I really hope you see the pattern of these values. They really repeat after the pi over 2. You'll see some get big, get small, get big again, or start big, go small. The point is you're going to see a repeating pattern in the cosine and sine, in the tangent and cotangent, in the secant and cosecant. So graphing the basic trig functions, the graph in the past we have plotted points and drawn a line or a curve through the points. We can graph trigonometric functions the same way. Let's look at the values of sine and cosine functions for values of x from 0 to 2 pi. Now the values I've chosen here, these are the standard ones we would memorize. 0, pi over 6, pi over 4, pi over 3, pi over 2. If you memorize these values in sine, cosine, tangent, cotangent, secant and cosecant, you know the whole thing. So we'll start off here. Let me scroll this up a little bit so I can have both the chart and the graph on the same screen. First of all, sine of 0 is 0. Sine of pi over 6 is going to be 1/2. Sine of pi over 4 is square root of 2 over 2. Sine of pi over 3 is square root of 3 over 2. And sine of pi over 2 is 1. Now the biggest sine is going to produce is 1. Sine of 2 pi over 3 is square root of 3 over 2. Sine of 3 pi over 4 is square root of 2 over 2. Sine of 5 pi over 6 is 1/2. So you'll see these same values. So it's peaked up here, it's going back down. Sine of pi is 0. Sine of 7 pi over 6 is negative 1/2. 5 pi over 4, sine of 5 pi over 4 is negative square root of 2 over 2. Sine of 4 pi over 3 is negative square root of 3 over 2. And sine of 3 pi over 2 is negative 1. So you notice it had those same values, now with negatives going down to negative 1. That's going to bottom out at negative 1, it's going to start going up again. Sine of 5 pi over 3 is negative square root of 3 over 2. Sine of 7 pi over 4 is negative square root of 2 over 2. And sine of 11 pi over 6 is going to be negative 1/2. And sine of 2 pi is going to be 0 again. And I probably should go back and give you the decimal equivalent. It might be valuable to see that, especially for graphing on this graph right here. And this is where we're going to put sine. Cosine is going to go down below the next graph, which I'm not going to be able to have this on the screen when we do that. Okay, here are the decimal equivalents, and you can just put this in the calculator. 1/2 is 0.5. I don't know the best place to write these. Maybe I'll put 1/2 here, which is 0.5. Square root of 2 over 2 is 0.7071. And really, how close are we going to get on this graph? I mean, it's not that fine of a graph. Square root of 3 over 2 is going to be 0.8660. I think that's probably enough. You'll see, I think you can put the rest of those in there with on your graph if you want. But that's the important thing to see, is that 1/2 is 0.5. And maybe I just should, I'm thinking what's the best way to do this. Maybe we'll just do this. 1/2 is 0.5. Square root of 2 over 2 is 0.7071. And square root of 3 over 2 is 0.8666. Because I'm thinking this, people might think this is a fraction, and we don't want to do that. Okay, so we'll leave it like that. Okay, so here we go. Here's our sine. Sine of 0 is here at 0. Sine of, I probably should label this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. This is the 2 pi mark. Halfway across, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is going to be pi. Now halfway for that, 1, 2, 3, 4, 5, 6, this is our pi over 2. I did this by these tick marks by pi over 24 on purpose. 1, 2, 3, 4, 5, 6. This is 3 pi over 2. That means this halfway mark is pi over 4. 3 pi over 4. 5 pi over 4. And 7 pi over 4. And then we have pi over 6 here, and pi over 3. 2 pi over 3 there, and 5 pi over 6. And yes, there is that kind of a gap there. Those values we don't have as standard values. And it's going to be, what's the next one? 7 pi over 6. And 4 pi over 3. And up here we're at 5 pi over 3 and 11 pi over 6. Okay, so we have all the values in there now. Start plotting. And I'm going to go with, this is 1, and we'll say 0.5 is right about there. I'll do that in blue. So pi over 6, sine of pi over 6 we said was at 0.5. Sine of pi over 4 is square root of 2 over 2, which we said is basically 0.7. So I'm just eyeballing this. It's not going to be perfect. If you want a better graph, the calculators do a great job. Pi over 3, sine of pi over 3 is 0.86. Pi over 2 looks like it's at 1. It's not looks like, it is at 1. So we have this curve. It's come up like that. Then it's going to start going down. 2 pi over 3 is going to be at 0.86. Then we're at 0.7. Then we're at 0.5. Then we're at 0. So it starts coming down. Seven pi over 6 is at negative 0.5. So here's our negative 1, and that'd be negative 0.5. Nope. Now 5 pi over 4 is going to be at negative 0.7. Then negative 0.86, and negative 1. So we have this kind of a curve coming down now. 5 pi over 3, start going back up. Negative 0.86, negative 0.7, negative 0.5, and then 0. And there's our sine curve. The sine curve is actually a very important curve. It's a sinusoidal curve. It's another of the formal name, sinusoidal. And you see this in lots of applications. One very important application in electronics, the AC current. In radio frequencies, they use the sine curves to represent the frequency and the amplitude. And even, I was watching, I don't like Grey's Anatomy. My wife asked me, can you watch Grey's Anatomy with me? Watch that. They're showing the person's heart rate thing. And oh, look, the sinusoidal curve's messed up, they said. And I cued into that because it's a math term. But okay, so that's the sine curve. Peaks and goes down, back up to 0. And it will continue this process as we went on. If we went on to a million infinity to keep this curve going. Okay, let's fill in the table for the cosine values. At least you'll have those values when we do this next one. So cosine of 0 is 1, so it starts at 1. And that's its maximum value. Cosine of pi over 6 is square root of 3 over 2, which is our 0.866. Sine of pi over 4 is square root of 2 over 2. Look, they're the same there. Cosine of pi over 3 is 1/2. Cosine of pi over 2 is 0. Cosine of 2 pi over 3 is negative 1/2. Cosine of 3 pi over 4 is negative square root of 2 over 2. 5 pi over 6, negative square root of 3 over 2. And cosine of pi is negative 1. So it started up high at 1, it's bottomed out at negative 1. It'll start coming up again because the smallest cosine can be is negative 1. Cosine of 7 pi over 6 is negative square root of 3 over 2. Cosine of 5 pi over 4 is negative square root of 2 over 2. Cosine of 4 pi over 3 is negative 1/2. Cosine of 3 pi over 2 is 0. And then cosine of 5 pi over 3 is 1/2. Cosine of 7 pi over 4 is square root of 2 over 2. And cosine of 11 pi over 6 is square root of 3 over 2. And finally, cosine of 2 pi is 1 again. So this one starts at 1, goes down, and comes back up to 1. We're going to graph this one next here. Let me clear the board. Same thing here, we have to label our cosine graph. This is the 2 pi mark, pi mark, pi over 2, pi over 4, 3 pi over 4, 5 pi over 4, 3 pi over 2, 7 pi over 4. Okay. Pi over 6, pi over 3, 2 pi over 3, 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 3, oh, it's over here, and 11 pi over 6. So cosine, as we said, starts out up here at 1. And then we're at 0.86. Then we're at 0.7, 0.5, and then 0. So my curve doesn't look that great. Should be up there a little more. Okay, now we're going to go down below, negative 0.5, negative 0.7, negative 0.86, and negative 1. So it comes down. And then we're going to start going back up again. And continuing. I'll be out of your way in just a second here. Now, if you're thinking, that looks a lot like a sine curve, but shifted, you're right on. This is a shifted sine curve. They are co-functions. This is shifted by 90 degrees, or pi over 2. So if you shifted it that way, you'd have a sine curve. So this high point lined up right here on the pi over 2. And this continues in this pattern, going to negative infinity and going to positive infinity. So I'm going to go to the next page. So pause if you'd like to spend more time on that. Now I've included the graphs of the sine and cosine from the calculator. And important things to recognize. This is pi. Here's 2 pi. I believe it's right there. This is pi over 2, and this is 3 pi over 2. So that's our sine. That's kind of what we had. Looks better from the calculator. Yeah, I'll just scroll that up a little more, huh? Here's our cosine. Didn't mean to do that. Okay. Again, we have our 3 pi over 2, pi over 2. Pi is a low point, 2 pi is a high point, and 0 is a high point. That's cosine. So then I decided to put them both in the same graph, and I went from 0 to 4 pi instead of 0 to 2 pi. And this curve here that's our sine. And the other curve is our cosine. So if you took this cosine and moved it over that way a little bit, all those points can line up. Move it by pi over 2, they're going to line up. Now we're going to go on to the secant function. So we're going to use the values we had from the cosine. Now I'm going to go through and fill in the decimal equivalents. So we're at 1. This is square root of 3 over 2. That's 0.866. Then we're at square root of 2 over 2. That was 0.7071. Then we're at 0.5, then 0, 0.5, 0.707, 0.866, negative 1. Oh, these are negatives. Negative 0.866, negative 0.707, negative 0.5, 0, 0.5, negative 0.707, and no, positive 0.707, 0.866, and 1. Now remember that secant is 1 over cosine x. So it's a reciprocal. So 1 over 1 is 1. 1 over 0.866 is 1.2. I'm just going to one decimal place here. 1 over 0.707 is 1.4. 1 over 0.5 is 2. And 1 over 0 is undefined. 1 over negative 0.5 is negative 2. And we have negative 1.4, negative 1.2, and then negative 1. Negative 1.2, negative 1.4, negative 2, and then undefined again. Then we have 2, 1.4, 1.2, and then we have 1. So if we graph this, notice it's undefined at pi over 2 and at 3 pi over 2, and those are places that cosine is 0. So 1 over 0 is infinity. I forgot my 3 pi over 2. That's over here. Okay, now it's a matter of the pi over 6, pi over 3. 2 pi over 3, 5 pi over 6, and then we have 7 pi over 6, 4 pi over 3, 5 pi over 3, and 11 pi over 6. So at pi over 2 and 3 pi over 2, we had undefined. So we're going to have what we call vertical asymptotes there. These are vertical asymptotes. In this case, we're going to define this point as 2. Here's 1. Here is 2, and here's 1. I do this on purpose because if you notice, secant's never going to be between -1 and 1. It's bigger than 1, including 1, and it's less than -1, but it's not between them. Okay, let's start off. We start at 1, then 1.2, 1.4, that's at 2. So it's doing this type of thing. It's going up towards that asymptote. Vertical asymptote. It's not going to touch that line. It's going to approach it. Then we're at -2, -1.4, -1.2, -1, -1.2, -1.4, -2. And then we're at -2, no, +2, +1.4, +1.2, and +1. And that is your secant graph. That's the secant graph. I believe you get to graph the cosecant one. Cosecant is going to be like this, but shifted a little bit. Okay, let's go ahead and go on. Talk about period of a function. I think there's some typos here I want to correct. Period of a function is a function f is said to be periodic. That means it repeats after a certain amount of time. If there is a positive number of p's such that f of x plus p equals f of x. For all x in the domain of f, the smallest such p is called the period of f. So the period of sine is 2 pi because sine of x plus 2 pi is sine of x. The period of cosine is 2 pi because the period of cosine of x plus 2 pi is cosine of x. The period of secant is 2 pi. Secant of x plus 2 pi is secant of x. Same thing for cosecant. Now here's the mistake. The period of tangent is actually just pi. And for cotangent is just pi as well. Okay. So tangent and cotangent have a period of pi. Feel free to pause. I'm going to move on here. So the next thing we're going to graph is a tangent function. So we'll have the sine, the cosine, and get the tangent from that. Okay, I'm going to go with the decimals here and just to abbreviate, make this quick. Fill in the chart, 0.5, 0.7, 0.87, 1, 0.87, 0.7, 0.5, 0, negative 0.5, negative 0.7, negative 0.87, negative 1, negative 0.87, negative 0.7, negative 0.5, and 0. For cotangent, so those values are going to be down here for cosine, excuse me. 1, 0.87, 0.7, 0.5, 0, negative 0.5, negative 0.7, negative 0.87, negative 1, negative 0.87, negative 0.7, negative 0.5, 0, 0.5, 0.7, 0.87, and 1. So tangent is going to be sine over cosine. We're going to be dividing. 0 divided by 1 is 0. 0.5 divided by 0.87 is 0.58. We have 1. We're going to have 1.7, then it's going to be undefined. Because 1 divided by 0 is undefined. Then we're going to be at negative 1.7. negative 1, negative 0.58, 0. Now negative over negative is positive. This is third quadrant. Sine and cosine are both negative. This is where it's going to be positive again. So 0.58, 1, 1.7, undefined. And then we're at negative 1.7, negative 1, negative 0.58, and 0. So if we graph this, again, I've got to fill this in. Here's our 2 pi our sine, or sorry, our pi over 6, excuse me, pi over 3, pi over 3, then 5 pi over 3, and then we're at 11 pi over 6. Okay. So notice we had two places where this was undefined. It's undefined at pi over 2 and at 3 pi over 2, as we saw before. With the secant, because again, those are places that cosine is 0 and cosine's in the denominator here. I'm just going to scale this from negative 1 to 1, these marks. And we change colors to red now. Okay, we start off here at 0. And then we're going to 0.58. Then we're at 1. And then we're at 1.7. So we have this curve going up, approaching the vertical asymptote. And then we're down here, negative 1, negative 0.58, 0, 0.58, 1, and 1.7. So we have this kind of shape going on here. Looks almost like a cubic function. There we go. And then we have, continue this process. Starts down here, we're up to right about there, there, and there. And we're stopping. Now, what I want to point out though is from pi over 2 to 3 pi over 2, that's a distance of pi. It then starts repeating after pi. This is finishing one of these off. This is half of it. Half of it occurs over pi over 2. So that's an example, or that should hopefully illustrate how one period of this is pi, where the other ones were 2 pi. Okay. Feel free to pause if you'd like. I'm going to move on to even and odd functions. Now this concept is something you've seen before, I'm very confident, but just to refresh your memory. A function f is even if f of negative x equals f of x for all x. That's like saying an example of an even function, something you've seen many times, f of x equals x squared. Well, f of negative x is negative of x being squared, which is x squared. So x squared is even. For an odd function, f of negative x would be the negative of f of x. So f of negative x would be, let me give you another one. Let's say g. G of x is x cubed. G of negative x is the negative of x quantity cubed, which is negative x cubed, which is the negative of what we started with. So x cubed is an odd function. A lot of people think, well, yeah, the power is even, the power is odd. Well, that's not really what it is. It doesn't have to be that, because these trig functions can be even and odd. Sine of negative x is the negative of sine of x, so that makes it odd. This is an odd function. Cosecant of negative x is negative cosecant of x. It too is an odd function. Cosine of negative x is cosine of x. That makes it even. Same thing with secant. It's an even function. And tangent of negative x is negative tangent of x, so it's odd. Cotangent of negative x is the negative of, there should have been a negative here, cotangent. It is also odd. So even and odd functions, our trig functions, will be even or odd. Let's talk about amplitude. Amplitude of sine and cosine functions. Given a fixed real number, a, the amplitude of a function f of x equals a sine x, or a function g of x equals a cosine x, is the absolute value of a. As we know, the multiplication of sine x or cosine x by a stretches it if a is positive or bigger than 1, and compresses it if a is between negative 1 and 1, vertically by a factor of absolute value of a. So the amplitude represents the distance between the x-axis and the maximum value of the function. That's our amplitude. It's that distance, the amplitude. The distance from the x-axis to the maximum value. That's our amplitude. If you have ever listened to the radio, AM stands for amplitude modulation, and it talks about the signal amplitude is changed to get the different sounds out of it. The radio signal, but it's converted through the radio. FM stands for something else. Okay, simple harmonic motion. If an object is oscillating and its displacement from the midpoint at time t can be described either by f of t equals a sine omega t or g of t equals a cosine omega t, the object is said to be, in simple harmonic motion. In either case, a is a real number and omega is a positive real number. The amplitude of the object, that is the maximum displacement from rest, is absolute value of a, and the frequency of the object's motion is omega over 2 pi. Hertz, that's number of cycles per second. Like those new TVs, I don't have one of them yet, but those big flat screen TVs, little panel, thin TVs, they are measured, they refresh by, it's measured in hertz. Some are 60 hertz. It means every second it refreshes 60 times. Some are 120 hertz and some are 240 hertz. So the more expensive ones refresh more frequently. Okay, as example 3, we're going to use the given information to construct functions modeling the described behavior. This part bugs me. When I have this happen, I have a ceiling fan that does this. A pull cord for a lighted ceiling fan is swinging back and forth. The end of the cord swings a total distance of 4 inches from end to end and reaches a speed of 9 inches per second at the midpoint. So when they get off balance, they can start swinging things. Find the period of oscillation. So let's draw a little picture of our ceiling fan. So we have this cord here in the middle, and it's swinging from side to side. total distance of 4 inches. From end to end, it reaches a speed of 9 inches per second at the midpoint. So the question, find the period of oscillation. So if it is traveling 4 inches from one side to the other, it is traveling a total distance to go back, so 4 inches over, 4 inches back. It is traveling a total distance of 8 inches for one period. So its speed is 9 inches per second. Now we know distance equals rate times time. Time would be distance divided by rate. So that's going to be the total distance of 8 divided by 9. So this is 8 inches. It's traveled going there and back, divided by 9 inches per second. So it's 8/9 of 1 second is one period. So the period is 8/9 of a second. Okay. That's it for the ceiling fan. Little tassels on this. Okay. Feel free to pause that. I'm moving on here. Period revisited. We know that sine and cosine and their reciprocals go through one complete cycle over an interval of length 2 pi. The modified functions f of x equals sine bx and g of x equals cosine bx both have a period of 2 pi over b. So note that the period is a reciprocal of the frequency. So if you have a coefficient to the x inside your sine, cosine, cosecant, or cotangent function, no, cosecant or secant function, it's going to be the period length of 2 pi divided by b. And for cotangent and tangent, it would just be pi over b. So let's talk about putting these things together. Amplitude, period, and phase shift. This is a concept we haven't talked about yet. Given constants a and b that are positive and c, not necessarily positive, the functions f of x equals a sine bx minus c and g of x equals a cosine bx minus c. We've seen the a and the b before, but not the c. Have amplitude, absolute value of a. We're cool with that. Period 2 pi over b. Okay, I think we're just saying b is positive. A could be positive or negative. Period is 2 pi over b. And then phase shift is c over b, the constant divided by b. And it's funny because phase shift is a concept that's used in science fiction all the time. There is some such thing as phase shifting, but they always use it to where people appear invisible, or they can go through a wall, but they don't go through the floor. Don't understand that one. Okay. Left endpoint of one cycle of either function is c over b, and the right endpoint is c over b plus 2 pi over b. So that would give you one complete period from c over b to c over b plus 2 pi over b. That's one period. Now, that's with our phase shift. So if c was 0, it would be 0 to 2 pi over b. Here is the graph of f of x equals cosine of 2x minus 3. So notice how the peak does not start at x equals 0. It is shifted by 3 over 2, 1.5 units. So it should start here, but its peak is there. Let's go on to example 4 here. Okay, determine the amplitude, period, and phase shift of each of the following trigonometric equations. So here we have y equals 2 cosine x. Only thing different here is this 2 is right there, so we have an amplitude of 2. Our period has not changed. Period is 2 pi because we have no coefficient for the x. And our phase shift is 0. For b, we're going to solve for y, divide by 2. Y equals 3/2 sine pi theta. So our amplitude here is the coefficient here for sine. This coefficient, that's absolute value of 3/2 is just 3/2. Our period is going to be 2 pi divided by the coefficient for the variable theta. 2 pi over pi, that's just 2. This is a period of 2. And our phase shift, well, there's no c, so the phase shift is 0. No phase shift. Okay, this last one in this example, we'll divide by 5. Y equals 8/5 times cosine of 2 pi x plus 4. Now I want to point out the standard formula was y equals a cosine of bx minus c. That's important, identifying these things. In this, a is 8/5. Our b is 2 pi, and our c should be minus c, so c must be -4, because minus a -4 makes a +4. So with that in mind, we have an amplitude of absolute value of 8/5, which is 8/5, a period 2 pi divided by b, that's 2 pi divided by 2 pi, which is 1. And a phase shift, this one's not 0, that's kind of exciting. Okay, it's going to be c over b, so -4 over 2 pi, or -2 over pi. That's our phase shift. Being negative, it's going to move to the left. On the last page here, we're going to go ahead and graph some. Yay, get a graph. So here we're graphing, and I don't know if you have this up here, sine of x minus pi over 4. So if we look at this, we have, again, g of x, let me rewrite this, is sine of x minus pi over 4. Our a is 1, our b is 1, and our c is negative pi over 4. So the amplitude's not changing. Amplitude's just 1. our period's not changing. 2 pi over 1 is 2 pi. But our phase shift is going to be pi over 4. No, sorry, c is not negative. It's supposed to be minus. C is positive pi over 4. That means it's going to go pi over 4 units to the right. It's the positive phase shift. So if I label this, let's call this pi over 2 pi, 3 pi over 2, and 2 pi. I'm going to put a mark in here for pi over 4. There'll be a mark back here for negative pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and just for fun, let's go on a little more to 9 pi over 4. And why did I go on a little further? Because we have a phase shift. Normally we'd start here at 0. Origin, it's going to be 0 here at 0 for x. But there's a phase shift of pi over 4, so we start over here. Normally we'd be at 1 when we're at pi over 2. But there's a phase shift, so we're at 1 at 3 pi over 4. Normally we'd be at 0 for pi, but there's a phase shift of pi over 4, so we're at 0 at 5 pi over 4. Normally we'd be at negative 1 for 3 pi over 2, but there's a phase shift, so we're going to be at negative 1 at 7 pi over 4. And normally we'd be at 0 at 2 pi. Now it's up to over here at 9 pi over 4. And so normally we'd be at negative 1 for pi over 2, negative pi over 2, but now it's going to be at negative pi over 4. So we're going to come up. Kind of missed it there. That's it. It's a shifted sine function. It's shifted to the right by pi over 4. Okay, so that was fun. So notice the next one we're going to be doing a vertical shift and a horizontal shift. That'll be next. So if you want to pause, go ahead and pause before we start moving things. So this is something we haven't talked about in this section, but it's something we've done in the past. We added a constant to our graph. So this graph is going to go up by 4. So our baseline here, this x-axis, what if we considered that now to be up a little further? I'm going to go ahead and call this 2, 4, 6, 8, 10. I'm going to change it to blue just to be consistent with everything else. So here would be our important values. So the f of x equals 4 plus tangent of the quantity x plus 3 pi over 2 means there's a vertical shift of 4. Amplitude still 1. Really, this does have an amplitude, but it goes up forever, so it's kind of hard to visualize that sometimes. Period is still pi. Well, here's what's interesting. We have a phase shift of negative 3 pi over 2. What does that mean to us? We normally would go from negative pi over 2 to pi over 2. And we go pi over 2 to 3 pi over 2. But having a negative 3 pi over 2 phase shift, it's going to go to the left 3 pi over 2. So when there would have been a vertical asymptote here At 3 pi over 2, it's over here now at 0. And we would have had an asymptote then pi units later, so now there's going to be one here at pi. And we would have had an asymptote pi units later. We still do. I did those in green before. Beyond that, it's still just a tangent graph. So it's going to cross right about there. It's going to come up, cross, and go up. Go up, cross, and there. And at this point, it's going to go up. And there's our tangent graph. So we shifted vertically by 4. We shifted to the left by 3 pi over 2. Okay, and that does it for 6.4. Please send me your questions.